All right, we're just a little bit past 1 o'clock. I think we're going to get started. It's great to see you. It's a wonderful turnout. I was just paging through, and I think I got 4 pages of my whole screen filled up. So that's exciting to have this many people tune in to this great forum. My name is Glenn Marzluff. I'm the general manager and CEO of the Delco Water Company. We're a large water utility that operates in suburban Central Ohio, suburban Columbus, Ohio area. I also serve as co-chair of the Sustaining Scioto Program committee, which is it's a subcommittee of the Mid-Ohio Regional Planning Commission, and we'll go into a little bit of that here in just a second. But again, I want to thank you for joining us today for this workshop on updating precipitate data for Central Ohio for the stormwater and flooding planning. I want to thank so much the Franklin County Soil and Water District for hosting and facilitating the event. We appreciate all their effort and getting this thing advertised, outreached, and getting all you engaged and on the Zoom call today. Also want to thank the State Climate Office of Ohio, the City of Columbus, the National Oceanic and Atmospheric Administration, and the Illinois State Climatologist for being here with us to present today. So again, Sustaining Scioto is it's a subcommittee of the Sustainability Committee for the Mid-Ohio Regional Planning Commission. And it was formed last year to implement strategies to address risks in the region's water resources that are related to climate change. We're excited to work with the City of Columbus, and they approached us and suggested that we consider this project to deal with the precipitation statistics and how that relates to their ability to plan local infrastructure. We recognize the need for data extends beyond our local jurisdictions here in Central Ohio and might be a more statewide, regional approach, or even beyond that, multi-states might consider participating in this. So we're excited about that. We hope that today's forum is enlightening regarding the need to use this data and the possibilities with it, reflects the weather trends that are driven by climate change, provides data resources, possible paths moving forward for creating and updating this data. So we're looking forward to the engagement here this afternoon on this effort. There will be contact information at the end and a follow-up information, an email to get some additional information from you and to get some response to the event today. So first, I have a small slide deck. I'm going to give you some context and background on this Sustaining Scioto project. And then we're going to have a couple of polling questions, and then we're going to get into the presentations. And we're trying to reserve a few minutes after each for question and answers, but there will also be some time reserved at the end if you're not able to get your questions answered in those periods. If you run out of time, or just there's empty availability for any more questions, right? So I am going to go through a little slide deck here to tell you a little bit more about the Sustaining Scioto program we have. So it's almost a decade old now. We started in 2011 with phase 1 of the project, and that was finished in 2014. And it really looked at this at the regional climate issues related, precipitation and flooding and everything related to this Upper Scioto watershed, which is a 3,200 square mile watershed, and that provides drinking water for nearly 2 million in our region. The original project had these partners, Mid-Ohio Regional Planning Commission. Again, they were the lead on it, along with the Ohio Water Development Authority, the USGS. We're going to go into some of the modeling they did here in just a second. City of Columbus and Delco Water, we were funding agencies, and Brown and Caldwell were the primary consultant that we used on that particular project. So the USGS, they actually developed just a watershed regional did some modeling for us both on expected temperature changes within the region for the next 50 years. As you can see, they continue to trend up, not surprisingly there, and also on precipitation, what we would expect there. And there we saw not necessarily a trend up, but greater variability on precipitation in our region. Lots more flashy events rather than what we've seen traditionally. So it took the results of the USGS data and looked at its impacts on different industries you see related here. Of course, water and wastewater. I told you the City of Columbus, that's where we were some of the primary funders, but also several other impacted sectors. And then ultimately, looked at the threats and vulnerabilities and how they related to these various things, including, for instance, damage to infrastructure is one of the things we're going to talk about today. It's one of the that planning for flooding that's going to be resultant of maybe any study that would come out of resultant of this information we're talking about today. And it developed short-term, mid-term, and long-term strategies. The final resultant. And the short-term strategy, one of the main things that the original plan created was this regional collaboration and public education, and that is this phase 2 of the standing side of subcommittee, which is in part of MORPC today. So that's just kind of a little context. This has been going on for a while. We've kind of been trying to be at the forefront of climate change and how that affects our region. And specifically today, this kind of came as a recommendation from City of Columbus that observed that maybe this that the hydrographic data that we have today is not entirely accurate, and we should kind of take a look if there's an opportunity to update that so we can have better data in which to plan for infrastructure and everything in the future. So with that, I'm going to ask Brooke to kind of launch the interactive polls.
Oh, and as soon as I said that, give me a minute. I think
we can do so.
Geez, I think one of my coworkers might have logged in, and now it's preventing me from doing that. So let me try to reach out to her. Maybe we come back to the whole questions here.
For a minute. I mean, is there any reason we shouldn't just circle back to that after the
We can just circle back.
Is that okay?
I think that's fine.
Okay. Well, I'm going to go ahead and introduce Art then, and we'll get started with the presentation. So, Art DeGaetano. Gaetano, that's what I meant to say. Art Gaetano received an interdisciplinary PhD focusing on climatology and horticulture from Rutgers in 1989. He was an assistant professor in the Department of Meteorology and South Dakota Schools of Mines and Technologies in Rapid City. He began his career at Cornell in 2001 as a research climatologist in the federally supported Northeast Regional Climate Center, which is at Cornell. He is currently a professor in the Department of Earth and Atmospheric Sciences and the director of the NRCC. The mission of the NRCC is to enhance the use and dissemination of climate information to a wide variety of sectors in the Northeast. He serves as the climate editor for Bulletin of the American Meteorological Society. Art, thanks so much for being here today. I'm going to stop sharing my screen so you're able to do it on yours. And just again, thank you so much. Maybe my screen's already been stopped. Is it stopped already?
I think we should be good, right?
Okay. Yeah. I was just saying a little bit something different. I'm going to be quiet. Art, thank you. Take it away.
All right. Thank you. Good afternoon, everyone. So basically, I'm going to go over some of the work we've been doing out on the East Coast, mainly in New Jersey, a little bit in New York, and a good part of it in the Mid-Atlantic in the Chesapeake Bay Basin, basically from the southern part of New York down through Virginia. And basically the work I'm going to present today has been an ongoing effort. So a bunch of different collaborators are part of this work, not just me. Several here from Cornell are big collaborators on the Mid-Atlantic Chesapeake Bay project. Have actually been some wonderful colleagues at Carnegie Mellon University in Pittsburgh. And then also involved in this is the RAND Corporation with Michelle Miro and Dave Robinson, who is the state climatologist at Rutgers for our New Jersey work. And you can see most of our funding has been coming from the Chesapeake Bay Trust, the states of Virginia, the states of New Jersey, NYSERDA in New York, and also NOAA. So I'm gonna set the stage. I think Glenn kind of set the stage really nicely. A recent headline here from the Washington Post, basically picking on kind of tying together two things: the latest thrust in new infrastructure that the US government is looking to undertake, and then also looking at some of the extreme rainfall statistics. And they particularly pointed out the Pacific Northwest, where the rainfall data that they're using to design their infrastructure is older than I am, to give you a kind of hint of my age. And I think basically also just to set the stage, this whole kind of idea of estimating rainfall extremes. I like to use the analogy It's like kind of trying to figure out the probability of the different poker hands you could get without not quite knowing all of the different cards. And the reason I use that analogy is we have a very limited rainfall record at most stations. And in many cases, we're trying to estimate the 100 or more year return period of storms with 30 or 40 or 50 or 60 years of data. So those would be the missing cards in this example. Just to give you a little bit of background of what we've been doing in our work, we use something that's called a partial duration series, and showing the values here for Boston, since it's in my neck of the woods. It's analogous to what NOAA does in their Atlas 14, but basically, if I take a station like Boston that has 72 years of record, I go to that record of daily rainfall and I pick out the 72 biggest values. So there could be some values that occur in the same year. We have to space them out by a certain amount to make sure that they're independent, but it would be quite likely here in, say, a case like Boston, where we might get a big rainfall event that falls into the partial duration series in the spring with a nor'easter or something like that, and then get another one in the same year as we move into September or October with a tropical system. To that partial duration series, we need to fit a statistical distribution. Generally, people use what's called the extreme value distribution. And really the idea is to take those individual observations and, number one, smooth them out to kind of eliminate the sampling variability. And number two, to allow us to kind of go out beyond the available period of record. So in my Boston example, again, I only had 72 years of data, but yet I need to figure out probabilities that maybe are at the 1% level, a 1 in 100 year storm. So the GEV is kind of given by three sort of parameters that I'll talk about a little bit. The first one, you can think of this as the mean of the distribution, the mean of that partial duration series. So basically in this case, if I start off with the black line and then that location, that mean increases, I get more rainfall on average. We'll see that whole distribution shift. The scale here in the middle is how squashed it is. So it's analogous to the standard deviation if we were talking about normal data. So again, if I made this more, if I increase the scale, I kind of spread out the distribution more, and there are more chances of getting extremes. And then I have a shape parameter, and that has to do with really how stretched out or not stretched out the tails are of the distribution. So kind of give you an idea, we're using, again, a method very similar to what NOAA uses in their Atlas 14. It's regional L moments. And really the idea here is when we look at data at a particular station, we use that station's location, its mean, and we allow that to change through time, or we kind of see how that changes through time. But the higher order moments, the scale, the shape, we look at that at a surrounding set of stations. And the idea here is those are more finicky basically for what might go on at any one particular station. So we try to get a nice regional average of those values as we would expect in the climate system. Kind of our methods kind of going through, we take our partial duration series, that's our sample. We fit our distribution to it. From that distribution that we fit, we can figure out whatever percentile we might be interested in. So if I'm interested in the biggest rainfall events, I might choose the 99th percentile, and that would say, boy, these are the storms that only have a 1% chance of occurring each year, or we can say that that's on average a 100-year recurrence interval. Once I fit this distribution to my sample of data, I can kind of use that as my background. And then I can use kind of a resampling technique, kind of a Monte Carlo approach where I randomly select data values out of this distribution. And that's kind of meant to simulate this idea of not having a full deck of cards in the poker hand. The distribution is meant to simulate the cards that I have, and I randomly pick kind of different shuffles out of that. So I get a good idea of the sampling variation. Typically do that 1,000 times to get, in this case, what we would have is we would have 1,000 values of the 100-year storm from each of these resampled distribution. and then we can make some inference on what this might look like going on. We can say, you know, have a little bit of a, what do I want to say here? You know, we're not just giving it one value, but we can kind of give a probability of where that rainfall amount might fall within the 100-year storm. And the point that I also here is looking at the data, you know, those ends of the distributions are called the tails. And it's very easy to fit the middle part of the distribution, something that we might call the 2-year storm. But when I'm way out there on the end and trying to get something like a 100-year storm, you know, the values kind of wag all over the place. So the fit to this one-to-one line, if I use a different method or I draw a different sample, are going to be a lot wider. So we'll see in some of the, particularly the projections for the future, that there's some fairly wide uncertainty bands on these numbers. So really in our work, we're answering 3 questions basically. And the first question is, you know, basically the premise in extreme value analysis for rainfall has always been to find the longest possible record that you actually can get. And that kind of makes sense. You're looking at these very extreme events, so you really want a very long data record. But what we find is that that works very nice if there's no trend in that location. So this would be, say, there might be year-to-year variations about this dotted line, but through time, basically the average of that partial duration series is flat. And if that was the case, having a very, very long record would be exactly what you wanted. However, in reality, what we see are these partial duration series are trended. There's more extreme rainfall events in the recent record. So the question was, if we use the longest period of record possible, you know, we'd be including these data values way down here that are very low, compared to really what might be more common today if this is the more recent period. So we might be skewing the record by using these very, you know, these oldest data records because they're not a good reflection of what the current climate is. So a pretty ugly graph, and I'll try to walk through it real quickly. Basically, what we said is kind of set our standard as having 150 years of data. And pretty much that's really the best you can do with most station records in the United States. And what I'm looking at are different storms. So a 5-year return period, a 10-year, a 25-year return period. And really, they all kind of say the same thing. So I'll focus up on the top one. The different colors represents different degrees of trends in my partial duration series. So does rainfall change very quickly through time, or maybe more subtly through time? So very quickly would be my gray line up at the top. More subtly would be the blue or the green or the red through time. And really where I want to be, if I'm doing everything correctly, I should fall in this little gray area here, which basically says, if I know what the real 5-year storm is based on 150 years of record, that says I should be off in my confidence 5% of the time if I've set it up that way. And then what I do is I go across this graph. I say, all right, well, how about if I really don't have 150 years? How about if I only have 130 or 120 or 100 years? How often do I kind of miss what that real value is out here? And as you can see, it's not too bad at 120 years. It's a little worse at 100, you know, and then as I get down, if I'm only using 30 years, I'm out of that band, you know, almost half of the time. So kind of really where we want to be is, this would be our argument for using the longest record possible. However, when I start adding trends to the data, see a very different pattern to these lines. Instead of getting better as I add more data to the record, especially those with the highest trends actually turn around and start to get worse. So in a nutshell, this blue area in the graph in the conclusion of this work said, boy, if we really don't know what the trend is in the data, if we're not sure that it's stationary, we shouldn't be going for the longest records, but we should be probably somewhere within this 70 to, if we can, 120-year time frame But keeping in mind in the records with the biggest trends, and there are many records in the US that have this 0.1% per decade change in their extremes, they really start to get worse, very soon. So maybe we should be limiting our record to something like 70 years. So that was kind of our conclusion there. The next thing is really maybe more the crux of what you're going to hear about or what you're interested in the workshop is how often should these extreme rainfall statistics that are in use be updated. The current values, I believe, for all of Ohio is the same as the Mid-Atlantic. They come out of NOAA Atlas 14 Volume 2, which has data that goes through 2000. So the question we were asked here actually by the state of New Jersey is NOAA Atlas 14 out of date for their reason? Should they be looking to update it? So our study domain is here. It does extend out as far out as Ohio and covers a good part of the Mid-Atlantic. We tried as hard as we could to simulate the methods that Atlas 14 uses, with a few subtle differences. And the graphics here are designed to show you basically, I think the take-home message is we do pretty well. We replicate their values. Pretty much anything with a black circle around it, we're within their confidence intervals. So we can't really distinguish our results from theirs in the case of the 2-year storm. In the case of the 100-year storm, the same type of thing, particularly across New York and New England, a lot of black circles, which means even out in Michigan, you can't distinguish our results from NOAA Atlas 14s. A little bit different as you move south, and this was actually a change in NOAA's methodology. They have very narrow confidence intervals in the Mid-Atlantic as opposed to New York and New England. So we tend to fall out of the confidence intervals. But again, about we're only off on average about 5% in that case. And then what we did was basically compared 2 periods of record. We basically compared the 1950 to 2000 record. That was our simulation of Atlas 14. We didn't go earlier than that is because we didn't want to compromise our analysis with some stations having earlier data and others not. So basically at all stations, and there's about well over 400 stations here, we chose this as our base period of record. And then we simply added the additional 20 years of data to bring this up, or 19 years of data to bring this up to 2019. In the box plots, what I'm showing is how the 2-year storm and the 100-year storm change for different durations. So kind of going across what this would be a 1-day precipitation accumulation, a 2-day precipitation accumulation, a 7-day accumulation, a 20-day accumulation. And really the box plots are meant to show the difference between these 2 periods. So we can basically take this to say by adding the additional 20 years of data, the values across all these stations, again, this is the broad area that even extends back to Ohio, on average or on median, regardless of what accumulation we're looking at, 1 day or 20 days, it's about 2.5% higher on average. At 50% of the stations, it's more than that. So basically, the way the box plots would work is 75 or 25% of the stations are above this. So basically at 25% of our stations in this region, the change has been more than 5%. And then if you can look on the opposite side of the scale, actually at 25% of the stations, the values have declined. So taken as a whole, there's been an increase in extreme rainfall in this adding these 20 years at over half of the stations. And we see a very similar pattern for the 100-year storm, not much difference in the change by accumulation period. A bit higher increases. There's more stations that exceed 5%, particularly out at the 20-day storm. So on average, we have seen an increase in these Atlas 14 values at over 50% of the stations across the Mid-Atlantic region. Why do these, what causes these differences? And more importantly, what causes some stations to have increases and some stations to have decreases? So what I'm doing is I'm comparing neighboring stations, and basically the numbers, this is a station in Massachusetts, and B would be a station that's right over the border in New Hampshire. And what I'm showing by the red line is the change in basically the, what am I looking at here? The 100-year storm. If I end the data in different years relative to Atlas 14. So my base is going to be 2000. So that would be the 1-to-1 line. So at this station, as I move forward, you get big changes in this 100-year storm that kind of align with these purple bars. And what these bars represent when they're purple is this is the highest value of rainfall that is in the partial duration series. So keep in mind, I'm starting this in 1950, so 40 years before these graphs start. And yet these purple graphs are the biggest values in that entire period. And what we see at both stations, this one in New Hampshire and then this one down here in Pennsylvania, we get the biggest increases in the 100-year storm. The more frequently we get these record-breaking or these biggest values in the partial duration series. And this occurs, again, at over 50% of the stations. At the few stations that go downward, what we see is a lack of these values, and actually more values kind of at the very end, the middle, kind of the lower end of the distribution. So we're increasing the length of this record, but really not adding any bigger rainfall events at these stations. So the trends, again, are occurring at most stations, but some of them do show still a downward change in the Atlas 14 values. Kind of broke this up by year. So in other words, what I would be saying here is if we kind of, I want to say, what do the current values look like relative to data if I ended it in 2015 as opposed to 2019? Ended it in 2010 and 2005, 2095, 99. So kind of extending the new data that I have. And to the left, we see the 2-year storm. To the right, we see the 100-year storm. This again is at all stations across that study domain. And really what we see is a downward, basically what we want to say is this is what we see is as the increases are kind of going in this direction. So kind of making this relative to the current period of time. So basically the record for today is basically, here's 5% greater than it would have been in 2000, almost 7% greater than it would have been if I ended in 1990. If I look at the 100-year storm, the same type of thing. We see this steady increase through time, reflecting the change in extreme rainfall through the period of record. We also did some significance testing, and basically we asked, what would be the chance of getting these big changes or changes this big if there wasn't a trend in the data record and we just added more data, we just sampled from more years? And really what we see is we get a big cutoff. There's really not too many significant values if we just leave off 10 years of the data. But when we leave off 20 and 30 years of the data, when I'm going up here to the middle and the top, we get a much higher percentage of stations that show a significant change. And the green dots are our significant increases in this analysis. So our real concluding point from this, which I don't have, is really it's probably pretty prudent to not let these extreme value analysis kind of just sit there and not be updated, but really the data suggests that updating these on a 20 or at the most 30-year cycle would really be warranted, particularly given the change in climate conditions. And then the last thing we did in our work in the Mid-Atlantic was kind of look to the future. You know, is the partial duration series, are the rainfall extremes based on data through 2020, you know, are they relevant for maybe infrastructure that people are looking to design and have it last till 2070? So we use downscaled projections from a lot of different climate models, basically 2 different ways, dynamically, kind of a model in a model, physically based, and statistical. Kind of went through this same process that we did with the observed data. And really what we come up with in the end is something we call a change factor. And really all it is the rainfall amount for the 100-year storm in the future divided by that in the base period, which we're defining as 1950 to 1999. This is the historical period in most climate models. So if we do that and kind of look at that across New Jersey, these are the changes we get looking at fairly high emissions at the end of the century. I'm looking at the 2-year storm, the 25-year storm, the 100-year storm. So if we look at the 2-year storm, we basically, by the end of the century, are looking at about a 15 to 20% increase across the state and kind of this part of the East Coast. If we move to the 25-year storm, start to see maybe a little bit more spatial pattern where it's about a 10% increase in coastal New Jersey and central New Jersey and the New York City area. But in the higher elevations of northern New Jersey and into the Catskills of New York, we're seeing changes that are more on the 20 to 25, or actually even 25 to 30% range. And then if we look at the 100-year storm, we actually see that same structural pattern and changes in the very high elevations of northern New Jersey and in through New England of on the order of 35 to 40%. Like I said, we looked at the confidence intervals. So this is my average 2-year storm. On average, like I said, 15 to 20% of an increase. If I look at a low end of looking at all these models and all these downscaling techniques, it's more like 5 to maybe 7.5%. If I look at the higher end in the darker blues for the 2-year storm, it's like 25 to 30%. Can do the same thing with the 100-year storm. And this is going back to my tail. On average, we're seeing something like a 10 in the light blue to as much as a 40 in the dark blue in the median. If I look at the low end of my projection, lots of kind of pinks, which actually are a decline in the 100-year storm. So many of our combinations show a decline. But if I look at the high end of the spectrum, I actually had to adjust my color scale, where in the low areas that we did see now, they were like 10%. But in this case, they're as much as 30%. And up into New York and northern parts of New Jersey, actually in excess of 60% of an increase in these ensembles. Kind of looking between the 2 emissions, lower and higher. So this is a 100-year storm, the median values for the end of the century. And basically, in either case, we're still seeing increases. The increases are more subtle in the low emissions case, on the order of maybe 2 or at the most 5% in through the city. See that same pattern here, but higher values in the RPC 8.5. We did look at some hourly data, but basically punted because there was a lack of consistency in what we saw from different durations. And looking at my time, the last thing is actually put this all together in sort of a nifty website, particularly for the folks in the Chesapeake Bay, where we were working with the NOAA RISA that covers that region. And basically the idea here is the colored area is the basin. The dots or the markers are the long-term Atlas 14 stations. So basically you could develop a change factor between the values you would use from Atlas 14 and what you might see in different storms, different emission scenarios, different periods of time going into the future. You could get it graphically as an intensity, duration, frequency curve, or you can get it in a tabular format showing the change factors by county and then the actual rainfall depths, not only the average values, but also the ends of the confidence intervals. So I've used up my time plus about a minute. So I'll leave it to the moderators to see if we're going to do questions now or at the end.
Thanks so much, Art, for that great presentation. I think we'll go ahead and hold questions at least until after the next presenter, if we have time then, and we'll see if we can squeeze them in at that point. They do have a chance to do the polling now. Brooke informed me that Kylie's on and she's able to share the poll. So if you don't mind doing that, please do so at this time. All right, I see one coming up now. What sector are you in? Give everybody about another 15, 20 seconds to respond to the poll. All right, maybe just another 5 seconds if you don't mind getting that response in. Appreciate it. All right, can we share those back? Here we go. The majority are in government, but consulting and academia, there's several others represented here today. And I think Brooke said there's a second poll. Is that correct?
Yes, there should be a second poll in there, Kylie.
Okay, here it comes. The question is your organization actively considering weather trends due to climate change in its current work? Give everybody about another 15 seconds to respond to this poll, and we'll share these results back. And then we're going to have Aaron Wilson up. All right, please respond now if you haven't already, and then we'll share the results back. All right, so 2/3, a little better than 2/3, are already starting to incorporate some of the results of climate change into their activities. So appreciate that. Kylie, thanks for sticking around and having those polls shared for us. This time I'm going to introduce Aaron Wilson. So Aaron is also a member of the Sustaining Setup Committee, and he's an atmospheric research scientist with the Bird, Polar, and Climate Research Center. He's also a climate specialist with the OSU Extension, which is the outreach and engagement arm of the College in Food, Ag, and Environment with the Ohio State University. Aaron is also on the State Climate Office of Ohio, and he's the Ohio lead for the North Central Climate Collaborative. Aaron's research focuses on climate variability, climate change, and applied climatology, particularly when they intersect with ag. Aaron, please go ahead and present your screen. I think it's up now, and I'll let you take it away. Thanks.
All right, thank you so much, Glenn, and thank you to everyone that's participating today in this great forum. I want to thank Franklin County Soil and Water for supporting us and all of the great folks who said yes when we asked to come and talk about this precipitation data. I want to do a couple things, just some background information on the State Climate Office of Ohio for those that don't know, and then get into a little bit of both broader aspects of this precipitation, the changes that we're seeing, but also some specific stuff about Ohio, and hopefully set up the next couple of speakers here in what they're going to show you today. So it's a pleasure. Certainly precipitation and changes that we're seeing are impacting many areas and many sectors of the state. These are just 3 examples that I've captured or friends have captured of recent impacts from heavy rainfall. We've got the Great Lakes that until this year, we were pretty much at a 2-year record high in terms of lake levels. This central figure here, this is I-71 at 665 on the south side. I sat in this line of traffic as this highway was inundated by water last summer, 2019. And then, of course, the ag impacts, which I hear a lot about and see a lot about. It's kind of great to be doing a little bit something different today, considering we've seen 5 to 7 inches of rainfall across the state the last 2 weeks. And a lot of my farmer friends are not happy right now. They're not happy. So hopefully I can get them some better weather. So yeah, Ohio State has retained the position of the state climatologist really without any formalized support since 1973. So it's been largely volunteer. There were several professors that kind of took the reins of that as well. And then recently in 2016, Brian Mark was tapped as the state climatologist with assistant Jim DeGaetano as well. And really, this has always been housed within the Department of Geography, at least since 1973. And we fancy ourselves as data stewards. We want to connect Ohioans with weather and climate information really necessary to improve lives. And I think that's exactly why we're here today. We have 4 areas of focus: climate communication, information services, education, and outreach, and then also research. So we kind of envelop a lot of the weather and climate information and data, both operationally, but also in a research sense throughout the state. And this is now an informal partnership between the Department of Geography, the Bird Polar and Climate Research Center, and also the Department of Extension. We have a lot of activities and a lot of statewide and regional collaborations that I think bring some strength to the state. Agricultural activities with my support from Extension as the climate specialist. We do a lot of events and a lot of interaction with communities throughout the state, developing resources and tools as well. Coordinating the drought monitor on a weekly basis. So that's really with the Ohio Emergency Management Agency, National Weather Service, many state agencies, ODNR, Department of Ag, et cetera. Regional collaborations. We have strong ties with the Midwest Climate Hub, NOAA Central Climate, Regional Climate Services, and others that really can help amplify, the Ohio-based message that kind of scales across the entire Midwest here. Other Ohio collaborations from sustaining Scioto to Columbus Climate Adaptation Plan that we helped construct a few years ago. A Sustainability Institute as well. And research, a lot of research integrating this type of modeling and climate variability, climate adaptation, and a lot of private industry are tuned into these changes as well. And so there's a really broad reach to the topic that we're talking about today with this precipitation data and update here in Ohio. And of course, we've got a lot of information and services. So I kind of encourage you to check out our website at climate.osu.edu. Follow us on Facebook and Twitter for all this information as well. So that's kind of a background on the State Climate Office. Now to a little bit more of the nitty-gritty in terms of Ohio and climate and thinking about these precipitation trends. I would start by talking, I didn't include my typical video that I show, which is a video of someone out walking their dog. Okay, and of course, if you walk your dog and the dog's on the leash, that dog is still meandering back and forth. It doesn't necessarily, the dog has some internal variability. It wants to go where it wants to go. That, even though you might be walking on the sidewalk. So that path along the sidewalk can define over time the mean path that the dog takes, for instance, but not exactly. That path doesn't capture those extremes, high or low, heavy rainfall or drought and light precipitation. And so that's really a good illustration for the differences between weather and climate. That weather is that day-to-day, fast-paced, continuous changes in temperature, wind speed, and moisture over short periods, short duration, short area or small areas. Whereas climate's those slower varying aspects over many, longer periods of time. So it's important to think about the context of weather and climate and put the idea of these extremes into that context a little bit. So if we look at what was, up until last week, the long-term, at least the National Weather Service 30-day normal period, and we'll talk about that in just a second, between 1981 and 2010, that was the established 30-year normal period that we were operating under. You can see the distribution and annual precipitation for Ohio here on the left. And this is, a pretty broad range here from less than 32 inches of annual precip close to the lake up there in Ottawa and Lucas counties to as much as 45, 46 inches, 47 inches in some of our Ohio River counties as well. So pretty broad reach. In Ohio and Columbus, Franklin County, really resting right in between there, anywhere from 38 to 40 inches really across our county. If we look at the seasonal distribution, May, June, July, those are the wetter periods, but and with drier months in October and also February. But generally speaking, we have a fairly fairly evenly distributed precipitation regime compared to areas like the desert Southwest that see seasonal monsoons and things like that. So that's really kind of what our baseline, our foundation of the type of climate we see from a precip standpoint. Now, if you've seen the news or you've seen it advertised, and maybe other folks like Dan Gelber or others on our local news stations talking about the changes in the National Weather Service climatological period that is used. Now, this really began in the 1930s. It was established as in a way under the assumption that climate wasn't varying, right? So we're going to look at this 30-year period to establish the conditions that we expect. We often hear climate is what we expect, weather is what we get. So that idea of changing every 10 years, basically you drop off a decade and you add a decade, was never intended to show climate change. This wasn't something that was designed to show climate change, but you do get hints and subtle changes that are taking place, sometimes not so subtly, that show you these shorter term changes as you add a decade and drop off a decade on this moving window, right? So it's important to know that these weren't established to show change, but we can see the change reflected between these two different periods. So now we're operating under the 1991 to 2020 time period. And what you're seeing here are differences, comparisons, in the change in annual mean temperature on the left and annual precipitation change here on the right in percentage. And so you can see temperatures rising anywhere from 0.5 degree to 1 degree in terms of our annual mean temperature. And along with that, we're seeing a good 5 to 10% increase by including the latest decade of our data and dropping off the previous decade. So at least in the 30-year period, we've seen the shift, we've seen changes to warmer and wetter conditions, which is consistent, as you'll see, with the longer term changes when we put it in a climate context. You can go to this website, you can see some comparisons between different core months of the seasons. So generally speaking, what we've seen over time are wetter winters, wetter springs, some variability when it gets to July, summertime, and also lingering in the fall as well. Because again, we see multiple changes here. It's really tied to temperatures as well. As temperatures warm, we see other changes taking place. But you can see here pretty strong trends in our winter and our spring, and then some different and variable conditions for summer and for fall as well. So this is the latest, I would say, this is the time series graph here looking at the seasonal normals now, 1991 to 2020 for Columbus. And so we can see, you know, January coolest and July being our warmest, pretty even distribution in rainfall here, especially May, June, and July being our heaviest months. And now here in Columbus, we're averaging 41.57 inches of rain per year. So before I showed you, we really fell in that 38 to 40 across the county. Now, because we've added the latest decade here, we're now closer to 41, 42 for the county. And you can see the seasonal distribution among the different seasons there. Still the most rainfall in summer, followed by spring, and then lighter amounts in fall and also winter. So to put this in a broader context, again, those are just, we can see those subtle changes by adding a decade or dropping a decade. But when we look at the longer time scales, when we set this all into context, I think it's really important to evaluate where we are. And possibly you could be asking yourself, why are we seeing, what are some potential reasons why we're seeing these changes in the precipitation values? Now, 2020 was the second warmest on the globe since 1880. Okay, so if we go back to 1880 with our time series, 2020 was the second warmest, and it was really statistically just shy of 2016 as the warmest year. 2019 was the third warmest for the globe. And if you look at the top 10 warmest years, they've all occurred since 2005. And I always like to use the statistics that, you know, if you were born after 1985, you've never experienced a cooler than average month for the planet compared to the 20th century mean. So again, we're looking at changes over the longer term 100-year record here. And spatially, this is what it looks like across the globe. We know most areas are warming. We still get areas that cool, and certainly month to month, we get some variability. Just this year, we can think about the different variability that we've seen just within 2021. Very warm December, January, very cold in February, obviously with the big polar plunge. March was Ohio's 12th warmest. Now we were still lingering with these cool conditions and snow on Mother's Day here in May. So that's, again, reflective of those differences between weather and climate. So when we think about, you know, a lot of times, a lot of attention's paid to the warming aspect, the temperatures that are increasing, you know, things like our greenhouse gases, the water vapor, the carbon dioxide, they just love that infrared radiation, that heat coming off the surface of the earth, absorbs that energy, the atmosphere warms. Okay, as far as greenhouse gases go, we have a ton of water vapor specifically in our atmosphere, and that is a function of temperature, right? So as our temperature rise, you often hear, although it's not scientifically exactly accurate, that warmer air holds more water. Water vapor is a function of temperature. So as our temperatures rise, right, we have more water vapor in the atmosphere as well. So CO2, like carbon dioxide, amplifies that effect by also increasing the number of greenhouse gas in the atmosphere. Atmosphere warms, it leads to evaporation, more evaporation of water from the surface into the atmosphere, and the atmosphere can warm even further as it's absorbing that radiation off the surface. So it's really important to pay attention to not just the temperature rising, but also the impacts and effects on the water cycles. As we, for instance, we get into July where very warm temperatures, or in the summer, we can evaporate water from the surface very quickly, right? And all of that water then is in the atmosphere that's available for fronts and other systems that can bring about those heavy downpours. And so it's not just the temperature side, but it's also this water cycle side and this hydrologic reality that we find ourselves in today. So if we do use the longer term trends, certainly what we've seen this week in the changing of the National Weather Service normals does fit, right, the context, or fits into the story of more longer term change. So we know from the latest National Climate Assessment from a couple of years ago that really today, compared to the early 20th century, we've seen 5 to 10% increases in annual precipitation across Ohio over this period of time. So about 5 to 15% here in Ohio overall. And there are just a number of different statistics and numbers that I can throw at you, and I'm going to do a little bit of that today, just a little bit, thinking about these longer term changes in these trends that we're seeing, to provide the context of why we need to more than what just Art already talked about as well. Very nice job of needing to update these extreme values, is this longer term perspective. Right. So if we look at, for instance, the observed 1 in 20 year return level precipitation for different seasons here across the Midwest, all of our seasons increase over this longer term period. Right. So we're seeing those heavier 1 in 20 year return levels increase, for instance, about 0.27 inches in the autumn period. Right. Also seeing large increases in spring and winter as well. So in context, a lot of different statistics that we can use about the changes in extreme precipitation are they're evident. They're really strong here across the Midwest. Art was talking about that 99th percentile, or you can think of it as a 1 in 100 year return here, kind of focusing in the top right corner here, looking just from 1958 to 2016, a 42% increase in those heaviest precipitation events in that 99th percentile there across the Midwest. Right, so very strong changes, 42% higher probability now across the Midwest today compared to earlier in the 20th century. Right, some nice resources that we can utilize. That we can utilize in terms of observed annual precipitation and long-term trends and extremes. If we're looking at our extremes here, kind of across Ohio, and the number of extreme events that we've seen, really we've seen a persistent change here in the total in the extreme events since about the mid-1990s, just here in Ohio. And looking at these other years that we see in our peaks for the number of precipitation events greater than 2 inches, there are really 3 other kind of years I can throw out that fall coincidentally within these peaks: 1913, 37, and 59. Right, and those are all major flood years in Ohio. So what am I saying with this graph? The graph is obviously we're never far from flood. The flood risk is high. This is what we're seeing today. And of course, flooding has a lot more than just precipitation involved, how we develop, how we store water, how we move water off the surface, etc. But that's where those decision-making and the water management comes into play, and it increases that risk. We often talk about the climate change as the threat multiplier, okay? So just ranking the top 10 warmest and top 10 wettest years for Ohio since back to 1895 here, 8 of the top 10 warmest and top 10 wettest years have occurred since 1990, right? So we can see then by adding that decade, the latest decade, to our record here for the normals, we can see the impact. It makes sense, that impact that we've seen on the earlier figures here. So thinking about years of 2018, 2019, 2017, all being within those top 10 years on precipitation. And 2020, even last year, not being that far off at 29th, I think, 29th wettest year for Ohio. So certainly the motivation to look at these extremes and update it for Ohio is there. And Art talked about the shifts and future changes here. Obviously, we think largely driven by, again, increased water vapor as well, but there are other changes and a lot of things when we have to think about why the precipitation changes. For instance, being able to ask questions like, is it more tropical activity? Is it changes in our overall weather pattern, shifts in our jet stream? There are a lot of areas of research that are still underway thinking about these changes. What impact does the Arctic sea ice loss perhaps play into all of this as well? But what we see in our emission scenarios, and we see into the future, is certainly wetter winters, wetter springs, even into the future, but then the potential for drier summers across much of the Midwest. You know, warmer temperatures, extreme evaporation rates increasing and leading to potential drier summers as well. So kind of just to sum it all up and kind of set up the next couple of speakers, you know, it's clear that our recent and long-term increases in annual and extreme precipitation are evident across Ohio. But more importantly, right, all of these changes that we see in precip impact a number of water-related management decisions across the state. And again, I'd like to thank the City of Columbus and Matt and Rob who, you know, to bring this idea together, to think about, at least to bring it to the subcommittee, to think about how we move forward here. And Matt will have a great presentation on this from the City of Columbus perspective. But then also, you know, this need to update the precipitation to account for the recent changes, while also maintaining that historical context. And so our friends at NOAA, Michael, thank you for being here as well, and Jim Angel from Illinois to talk a little bit more about what they did for Illinois just a few years ago, or actually more recently than that, just a couple of years ago. So with that, I will turn it back over to you, Glenn, and appreciate the time.
Aaron, thank you so much. Fabulous information. Again, we're running short on time, so I think we'll go ahead and just step right into the City of Columbus presentations. I'll go ahead and introduce both Matt and Robert, and then if we have some time, we'll take some questions before our break, and we'll hold that break time firm, make sure everyone has a chance to do whatever you need to do for that 10 minutes, right? So City of Columbus, first we've got Matt Repasky and then Robert Priestas. So Matt has been working in public service his entire career, has 23 years of water resources experience. He graduated from The Ohio State University with a degree in ag engineering and spent the first 10 years with ODNR with the dam safety program. And then he spent 7 years managing projects on behalf of the Division of Watercraft and ODNR to construct marinas and improve boating access to Ohio's water resources. For the past 6 years, he has worked with the team at Columbus to protect our water resources from pollution as an engineer and manager in stormwater and regulatory management section. And Rob is going to be also presenting as part of this. Mr. Priestas currently serves as the Assistant Administrator for the Division of Sewage and Drainage with the Department of Public Utilities at City of Columbus. His responsibilities primarily focused on the sewer collection system, which includes the city's Sewer Maintenance and Operations Center, pretreatment programs, stormwater regulatory compliance, plan review, and all stormwater and sewer system engineering functions. The entire Division of Sewers and Drains consists of approximately 450 employees with an annual operating budget of $270 million, including the capital debt service. maintenance and operations. So with that, I'm going to give it to Matt or whoever's going to take the lead here with City of Columbus. And thanks so much for bringing this matter to our attention. I'm really excited. We have over 100 participants today. So clearly you hit a chord. Thanks, Rob.
Nope. Thanks, Glenn. Appreciate you having us here today. Really like to thank MORPC as well as Franklin Soil and Water Conservation District. I'm going to kick off the discussion just a little bit with a brief overview of DOSD, our mission statement, some policy that we have in place, as well as a recent wet weather response. And I'll turn it over to Matt to talk a little bit about, what is changing, why be concerned, and then what are those impacts on our regulation, design, and operation. So Matt, if you could advance the slide, please. Again, just a quick agenda. We'll do a quick overview of the DOSD, our mission statement, some policy that we have in place, as well as a recent wet weather response, and then kind of look at those items where change might be occurring and why that's important for our teams. Matt? Quick overview, Division of Sewer Drainage. It's comprised of a 5-county treatment area. So we've got 2 treatment plants. Jackson Pike is the smaller of the 2, roughly treats about 45% of our annual sewage flow. And then also Southerly, which is a larger of our 2 plants, treats just about 55% of our average daily flow. We also have a composting facility that helps manage the biosolids from our treatment process. And I believe that facility actually achieved 4 years of 100% beneficial reuse of those biosolids. Matt, if you could advance, please. More the heart of where we're discussing. We've got just about 6,500 miles of sanitary, combined, and storm sewer pipes. Just to put that into perspective, that is the same mileage as driving from Columbus to Miami 3 times. So it puts the scale of our infrastructure in perspective. We also have 17 sanitary sewer pump stations. Actually, I believe that just bumped up to 18. 15 storm pump stations, 5 air quality control facilities, and really, and the last Franklinton flood wall, which is really connected to what we're discussing here today with concerns about flooding, climate change, and rainfall intensity. Matt, next slide, please. So our mission statement, to be a public utility dedicated to promoting the health and economic welfare of the Columbus metropolitan area by providing efficient, environmentally responsible management of the area's waste and storm sewers. Now that's a big job, it's a big task, and really, what we'll focus here today is kind of how we address the storm sewers and our stormwater management policy. Again, big question, policy and enforcement, right? How do we do this for storm sewers, design, and stormwater management? Our department realized that a lot of the issues that are caused by flooding and erosion are actually created. A lot of those can be created through development. Knowing this, in 2006, the city implemented its first stormwater drainage manual. That manual dedicates itself to identifying requirements for stormwater conveyance, stormwater quantity control, as well as protection of environmentally sensitive resources such as wetlands and floodways and floodplains. So we want to ensure that we're conveying and controlling stormwater in a safe and responsible manner to meet the water quality goals of the division. The large struggle is making sure that our policy remains sustainable to achieve our goals. Even though that policy or that manual was implemented in 2006, it was subsequently updated in 2012, and we actually just finished a 3rd revision that will be effective here in just a few days in 2021. But that is a collaborative process. We as the city have goals, and we also realize we have a lot of stakeholders in the community, including designers and developers that are very interested and impact their daily operations and business. So we make sure that is a very transparent process. But we get the question all the time, are you considering climate change? And absolutely, that's something our office is concerned about. And I think that's why the conversation today is extremely relevant. Yeah. A recent a couple of wet weather responses that we had that really tie into the conversation today occurred in spring of 2020. We really had 2 significant events that occurred. One towards the end of March, right around March 20th, and then the second in May of 2020. The first event, we saw rainfall depths ranging from 2.5 all the way up to roughly 4 inches. And then, the event just a short 2 months later, less than 2 months later, we saw, significant flooding and actual implementation of our flood wall, where we saw rainfall depths occurring anywhere from, roughly 3.5 almost up to 6 inches in less than a 12-hour time frame. And just to note that event on May 19th of 2020 actually is the 10th highest river stage level that we've got on record at our Frank Rhodes gauge, which helps drive our Franklin flood wall. So again, just kind of reinforcing that question, what is changing and are we accounting for climate change? So with that, I'll kick it over to Matt to present a little bit on what they're seeing on the climate side.
Thanks, Rob. So you saw some of this from Aaron earlier, but I saw this data come out last week and I saw this graphic, and I think that as kind of somewhat at my level, looking at regulations, looking at some maintenance, kind of in one picture, it really sets, it really shows the trend. And, it's just, there's no question we're seeing more rain. And you kind of say, so what does that really mean? But it got my attention and it got me thinking, and it was really good timing for this forum. And so I did look at the data, and I think Aaron had too. I looked a little closer, but so, what does it really mean here in Columbus and the more recently? And again, I haven't performed the statistics that Arthur and others have done, but, from a simple view, I can look at it and see, we've got a trend here going from 39 to 42. And then if we just look at the last 15 years of data here in Columbus, we're 43.5. So that is on the, that is on a calendar basis, not a water year, and it's not looking at peaks or intensities, but it is saying that there is more rain. And so, I think as a manager and a stormwater program, it's something that gets my attention. And, certainly I'd encourage you can go look at this data, for your local area and see, because of course, it is going to be area dependent. And then I also saw this line, which is from Atlas 14 Volume 8 from our friends up north, where they had gone through an update not terribly too long ago, but really it sets it right there. I think this quote is it, right? The precipitation frequency estimates used for stormwater management do not accurately reflect the depths falling during precipitation events in Southeast Michigan. In reality, rainfall depths are greater, 3 to 32%, than what's being designed for, especially for the larger storms. And, I think that is the challenge, or at least that's what is sitting here in front of us in Columbus and in the surrounding areas as well. So if you've been to probably any water resource, stormwater management conference in the last 8 years, you've heard about, surely you've heard Columbus present on Blueprint. But if you haven't, kind of in a nutshell, the Blueprint is our program where to address sanitary sewer overflows, specifically in some of our older neighborhoods, we are disconnecting the downspouts and sump pumps that were previously being discharged to that sanitary sewer, and we're redirecting that water to the storm sewer system. And as part of that, what we are doing is we are installing a lot of green infrastructure, rain gardens specifically, within the city's right-of-way. And so there should be some, there's both a water quality treatment to that aspect, but also there should be some attenuation of that runoff that otherwise would have gone untreated. And so in our partnership with Ohio State University, we have a lot of data. It's very important to the city to monitor the performance of this. I mean, we're going into a residential watershed, a residential neighborhood, and installing hundreds of rain gardens. We really want to have an understanding, because this is a long-term project. It'll span a few decades. And there's a significant capital investment in it. So as we went through the first few areas, we had partnered with Ohio State to really study it. And so I pulled this, this graph from their report that they had produced for the city last year. And so what you can kind of see in this graph, the steeper the line, what that means is that there's more runoff being generated. And so except for 2018, which kind of jumps over the 2019 number, but 2018, I believe, is the wettest year on record. Otherwise, you kind of see that trend. Again, we start with 2016 and we're working our way up to 2020. That line's getting steeper. And initially when we saw this, and Ohio State kind of put it in the report, it was a kind of a uh-oh moment, because if we are installing green infrastructure that is supposed to be attenuating runoff, then wouldn't we expect to see these lines get a little flatter? I mean, I think we would have less runoff for a given depth of rain. But the lines don't say that. Now, thankfully, Ohio State's able to look at the data, and then when you correct for that additional, the increase in precipitation, we actually do find that the rain gardens are having the impacts that we expected. But as far as just establishing a trend, I mean, this is another example of where this information that if you want to look at on a national level, global level, state level, or local level, I mean, I can look at it on a project level and I can see where this change in precipitation, the intensities, and the total volume are having a direct impact on the projects that we're putting in the ground. There's something else that occurred when I was kind of preparing for this talk, and I kind of wanted to think, what experiences do I have, what perspective do I have from where I sit today, what I've done that would be of interest to everyone, why do I care? And so it got me thinking about my career and just thinking about all of the flood events that I've been a part of in response somehow. And so, I think back to 1998 when I started and traveling out to the Muskingum River and doing high water marks, which was always eye-opening, from the flooding aspect of it. I'm kind of looking like 4 feet off the ground and somebody taps my shoulder and says, no, you need to go up further. And I'm looking up on a second story window and there's the high water mark. And, you carry that forward. I think back to, looking at in 2010, so I'm doing projects up at Delaware Lake, and the parking lot is about 30 feet above the normal water surface of that lake. And I'm wondering why, when I'm doing relocating the floating docks for storage, why they're being anchored 30 feet above the water surface. And well, in 2010, I saw it firsthand because they were floating, and so that's just the kind of reaction we get on some of these reservoirs in some of these areas. And then I've got bolded in there in 2005, just because that was Katrina, and I'll touch on that a little bit more in a moment. And then, as Rob pointed out, we've had some big events more recently, and the impact there, like in 2019 and 2020, my involvement there was more from the response side on the active construction sites. One thing my career in public service has taught me is that you don't ever want to be on the front page of the paper. And, it's happened a couple times here, and it wasn't my project per se, but the city of Columbus was, because we had sediment controls installed on a construction site, and then we had this major rain event that caused flooding, and there were cars that were flooded out. And so that's something that you just don't want to see. So now, as we take this data and move forward, I mean, we do have preemptively, we talk to contractors, think ahead. If you've got rain being forecast, you may need to adjust those temporary sediment and erosion controls you have. You may need to remove them, let that rain event pass, and then put them back in place, because otherwise, what we have, or we have controls that just aren't being designed with necessarily the right data to begin with. And so really, this isn't going to be, certainly isn't a thoroughly researched legal approach, but when I think about liability, as I said before, back in 2005, when I go back to my dam safety days and I think about conversations that I would have. So as part of that, we would go out, we do an inspection of a dam. We would produce a report, and we would provide that report to the owner, and that report would list the deficiencies that dam had, where it failed to meet what the current standards were. And very often an owner would say, okay, this is great, but this looks like it's going to cost me tens of thousands of dollars. What happens? What is the state going to do if I don't take any action? And I think at the time, the reality was, part of the conversation would be, we did have, if I'm remembering correctly, around 1,800 structures that were within our jurisdiction. And we just didn't have the resources. I could tell an owner, we may not have the resources today, to pursue our full legal remedy on every single situation. But what I would tell them is, I said, but think about this. Imagine there is a rain event. Imagine there is flooding that occurs. And somewhere downstream of your property, downstream of your dam, there's an impact, a negative impact. Now, people can sue for anything. There's nothing stopping you from filing a lawsuit. So imagine if that owner looking and says, there's a dam, and they file a lawsuit against you. And so you're sitting in court or in front of a judge, and you have a report with data in it that says there's some deficiencies here. And even if your dam nothing failed, nothing went wrong with it, if you took no action based on that data, what's your perception? You as an owner need to decide, how do you feel, how are you going to feel in a hypothetical situation? And so, I pull that back to same thing here as a municipality, as a government entity, the same thing here. We each have to evaluate kind of the circumstances that we have and kind of decide, well, how do we feel about it? How do we feel about not doing something? And so a lot of this, as these values increase and whether we modify our design standards to reflect those values or whether we use the ones that we've been using for a long time, using old data, there's going to be a cost increase. And so some entities have taken upon themselves, to file lawsuits over that. And that's just why I've listed these two, where they're trying to recoup the cost. They're responding to that impact by going after the corporations that they believe were contributing to that. And I'm not going to dwell on that one, but so thinking again too, that no action, I think one thing that's telling again that came out of Katrina is that there was at least a decision for a period of time, maybe it was 3 months, 6 months, where, where a lot of governments, we have that sovereign immunity, but there was a period of time where a judge found that did not apply, that there was negligence on behalf of the US in managing the levee system and that they were not shielded. That was, overturned on appeal, but for me, it's still significant to think that, it did happen briefly, maybe, and it could happen again. And so again, as an entity, you need to kind of consider your situation and how you, kind of feel about some of these concerns kind of brought up here. So more directly though, if we have increasing peaks, we have increasing intensities, we just have overall increasing volumes, where does that apply here in Columbus? And so that's through our stormwater drainage manual, which is really a regulation that has a lot of influence on how properties are developed in the city and in the surrounding region, as our manual is kind of used as guidance by others in the area. And then the other aspect would be, we do have a stormwater utility where we do collect fees from the users of our system. And those fees are based on an assessment of the cost for us to maintain that system. And so I would make the argument that we have two kind of things going on. So if we change those design values, we definitely are going to have an impact in design. You're going to see, potentially you'll have a need for larger storm sewer pipes themselves. Your post-construction stormwater control practices for detention and possibly water quality would need to be larger. And it even impacts that roadway design where your quantity of inlets, it's all based on your return intervals and the spacing of that. So if you have to have additional inlets, again, you're going to have additional cost in those projects. We may also start seeing persistent flooding in areas that we hadn't seen it before, and a pump station becomes part of that calculation. Do we need to install it or not? And so in the end, you're definitely going to see kind of up front, you're going to see that impact. If you do modify your values, you'd see an increase on that cost of construction. And I would say whether you modify those values or not, you're definitely going to see an increase in the cost of maintenance. I think it really doesn't matter if you, if you don't change those values. The fact is your infrastructure is going to see more wear and tear. And I already talked about, like on the sediment and erosion control practice side, there's just going to be more management. We do have a lot of, response that my group does when an event occurs and those practices, those temporary practices are overwhelmed. And then, we see it in the roadway, we get a complaint, and then we're going out there to address that, make sure the owner addresses that. And then the same with those permanent control practices. If you kind of look at the kind of a simple way of viewing it is that whether you have an increased peak or you have an increased intensity or you have just an increase in volume over that year, the idea is the more rain, the more runoff you have, the more runoff you have, the more loading you have onto your practices. And with the more loading, since a lot of these practices are like filters, the more you load them, the more they're going to fill up and need to be maintained. And for some of our practices, especially when we talk about the infiltrating practices, I think we all put them in the ground knowing that there is kind of a point in time where we would expect to have to kind of do a full restoration of them, completely remove that filter and put it back. Now, I think there's still a lot of research. We don't know exactly what that number is yet, what that year is, but I would imagine, again, it's going to be location specific. We're going to see that increasing load and we're going to see that increasing demand and an increasing cost on our maintenance side. So going back, one way to address that increased maintenance cost would be if you push it on the designer, push it on the owner to factor that in. You know, so if we adjust those rainfall values in our regulation, and it's addressed more on the front end, then on the back end where the city becomes responsible for some of these practices, maybe that would reduce our costs we otherwise would have incurred. And so I think what we'll see later, you know, we've kind of laid the groundwork so far in the presentations as to what's happening. I try to make that connection to, you know, why as a government entity it may be important for you, why as a designer it's important to consider. And then I think the next question where we go is what do we do about it? You know, I talked about that on the regulation side, but some of our following presentations are going to get into kind of those actual steps that we may, you know, individually or collectively be able to take. So thank you.
Matt and Rob, thanks so much for going through that. We do have a couple questions. We have a little bit of time, so let's try to address those before we go to break here. So I'll try to interpret a couple of these. A couple of them have to do, first one has to do with a blueprint project, and kind of the question is, are switching the downspouts and the sump pumps from those neighborhoods from going directly to the sanitary system out into the storm or an overland flow? Is that, do you feel like that's a contributor to the increases you're seeing in the overall peak flows?
So no, that the flows that we're seeing there are, so we have both, we have monitoring installations, both in some of the individual practices and then at the watershed as a whole. But we've also accounted for that in the analysis. And so when we look at an individual rain garden, that's factored in, and we can filter out those additional flows coming in. The idea is we can take the measurements of the individual practices, and we can scale those to the watershed, and then you can correct for that shift in where that flow is from where it was going into the sanitary into the storm. Okay.
Thanks, Matt. And then there's another question specifically regarding the drainage manual. And pardon me, I'm not a technical expert on this stuff. But I guess there was a switch from called the Huff Angel Midwest Atlas to the NOAA Atlas in 2014. And that tended to have the larger storms had a decrease, I think, in the new Atlas program. Talk to us about that a little bit. Trying to see the specific question. Increasing the storm depths for use in the Columbus. Are we showing an increase in the design storm depths for the use in the Columbus manual? And I think they're relating to the change there.
So I guess the question, maybe I don't understand the question. So that switch, if we're talking about going from Bulletin 71 to Atlas 14, is that what they're asking? Can we tell?
Somebody else can have to ask this question because I'm not capable of refining it anymore.
Yeah, so what I may have to do is take that question and do a little research. I think if that change occurred, it was before I started about 6 years ago with the city. So I'll have to look back, you know, at our historic, what we actually did in the past. I mean, I have read some papers, and maybe one of the other presenters will talk about it, about looking at, I think in the state of Illinois, between Bulletin 70 and Atlas 14 data. And there were some arguments wouldn't be the right term. There was, you know, I think in that case, the Bulletin 70 had higher values than the Atlas 14 data, but I would need to look further to see how that applied to Bulletin 71 in Ohio. It's just been too long since I looked at that.
Okay, yeah, I think you did interpret the question directly. I got a follow up chat here that did say the Bulletin 71 is part of that. That it described before. There's another question about best management practices. Well, increased runoff, we start to see changes in the BMP design that are protective of receiving storm structure. So I guess the question is, are we going to start having to upsize the BMPs to be able to capture larger events? I think that's what David's trying to get at.
Okay, so I think there's a couple thoughts, and maybe I need to step back a second. So we have with our new stormwater drainage manual, we sort of introduced the term stormwater control practices as a broad category, and that captures both detention practices as well as water quality practices. Water quality practices kind of set, that design set by the state, and it's a fixed value. It's not really rainfall dependent from one perspective, unless they were going to revise that value, again, based on these trends. And we did see a couple years ago when they went from 3/4 of an inch to 0.9 inches. But if we're talking about protecting those practices through the temporary BMPs, and could those need to be larger? So that is something that, as a designer, there isn't a prescriptive return interval that you necessarily need to design for, but you are looking at that data, at least not on all the practices anyway. But so you are looking at that data to make that decision. And I think that if, as a designer, you are going to say, if I'm going to put a filter on an inlet and I'm okay, my 6-month construction project, when I think about it as, the odds of that happening with a 10-year return period, I'm willing to live with that. I think the owner can live with that risk. If that 10-year return period date is actually wrong and it's really more like a 5-year return period, then you're just not making a correctly informed decision as to what kind of practice you're putting there.
Okay, Matt, I think, so there's a follow-up question, but I'm going to hold that maybe till the end because I do want to protect our break period here. We're at 2:25, so we're going to start back again at 2:35. We'll take a few minutes breaks. Thanks so much, Rob and Matt. Great presentation. Obviously, there's a lot of interest. There's some follow-up questions that'll probably come your way during our final Q&A period. So we'll see you all in about 8 minutes. Thanks.
All right, thank you.
Thank you.
We're going to get started in just another minute or so. You can all get back on if you're not there. All right, our next speaker is Michael St. Laurent. Mike is a meteorologist working at the Office of Water Prediction's Hydrometeorological, easy for me to say, Meteorological Design Study Center. He's worked on NOAA Atlas 14 since 2012. He has been involved in publishing volumes 8 through 11 as well as many other NOAA Atlas 14 research. Michael received a bachelor's in meteorology from Leiden State College and his master's in oceanography from the University of Rhode Island. Mike, thanks so much for being with us today. Appreciate you.
Thank you for having us. So got quite a few things to go through. Oop, is my screen sharing? Okay, good. I also have our division director, Mark Glaudemans, on the phone. He's going to jump in towards the end to talk about a little more things of the future of Atlas 14. I'm basically going to go through the background of mainly volume 2, which it covers Ohio, just to show what kind of was the status quo for Atlas 14 in the area. And then I'm going to go through to the future and some of the things we want to work on in the future. So as you know, Atlas 14, we developed that at the Hydro Design Study Center, or HDSC, in the Office of Water Prediction. Currently, we assume a stationary climate in these Atlas 14 volumes that you can see here. Volume 2, like I said, covers Ohio, and that was published around 2004, mainly had data up to about 2001. So some of the applications, as we've seen, are engineering, design, and infrastructure, as well as some other aspects of assessing the severity of some storm events. And just I have a few examples here if anybody's interested. So on our website itself, we provide digital downloads of gridded information for the precipitation frequency estimates, some geospatial maps, and sort of a point and click interface that gives you a table information as well. So for specifically volume 2, how were these estimates calculated? I'll go in these a little bit more detail, but it starts all with the data, of course, the data collection. We then extract our annual maximum series, which is the highest event per year. So assuming you have like a 30-year uninterrupted period of record, you would have 30 values from that specific station. We do some quality control, then we derive the depth, duration, frequency curves and the frequency estimates, and then we interpolate these to a grid. And then we go through some peer review where we ask some agencies to provide feedback, do some revision, and then we publish all these products on our website. So a little more detail, I'll start with the data itself. So for volume 2, these are a list of the data sources, and the vast majority of the data comes from NCEI right here, or formerly known as NCDC. But there is a few other data sources. But just for reference to a more recent volume, volume 11 in Texas, we have quite a few more data sources involved with this. We have many state, local, and federal agencies, as well as NCEI themselves. In the 2000s, early 2000s, mid 2000s, they did a significant modernization and digitized a vast amount of data, present and past data. So I guess the point here is that there's a lot more data in the last 20 years, not just federal data, but local and state agencies have invested in monitoring significantly. So for volume 2, these are the approximate amount of stations here, or these are the number of stations used in volume 2. You can see that most of the stations were used at a daily duration. Then we have some sub-daily stations. The first step is to just examine the stations themselves for their latitude, longitude. You'd be surprised how many stations are actually not even placed in the correct location when you go to download. So we fix those. We delete duplicate stations from different databases. We try to merge stations that are very close together and have similar statistics. Then we remove, we try to screen stations that have a sufficient number of data years, which I'll talk about that uncertainty a little later. We usually try to get more than 30 years of data, but this is relaxed for certain areas if if it's a data sparse area, specifically at sub-daily durations. So for volume 2 on the left here, we have just the spatial coverage of daily stations that were retained. And then on the right are sub-daily stations that were retained. So we have all these stations, daily, hourly, and minute stations. We extract the annual maximum series, and then we want to quality control these values. So what we do is at the station, we'll sort the values and do statistical analysis and mark low and high outliers. And in this case, we don't automatically delete high outliers because they're valid sometimes, or most of the time they're valid. But in this case, this 15.1 inches was actually supposed to be a 1.51 inches. So we would remove this, and then as you can see, this would have a significant impact on the precip frequency for this location. On the low end too, you'd be surprised that low outliers can actually make these fits here sort of tail off and flatten. So they're just as important as high outliers. For volume 2, you have all these annual maximum series data at different stations, but to get more confident estimates, you want to pool together data from nearby stations. In volume 2, the way they did that is to cluster stations together spatially like this into distinct regions. So for instance, you could see this varies greatly. So this 52 region here has a pretty large area and a lot of stations in it. But then you go to this Northern Illinois, and the Aurora area has a very small region, 54. So you can see there's a lot of variation in the region size for the volume 2 regions. For more recent volumes, this is shifted to regionalization, where you go station by station and make a distinct region for each station itself, sort of like a rolling window rather than discrete regions based on space. They are obviously close to the target station. However, they usually are smaller in the number of stations. So on average, 10 to 20 stations, where as you can see in the previous regions, they can be up to somewhere like 50 stations. We feel this is a good trade-off between having too large of a region, because this actually decreases the variability of the data, which can actually lower your estimates, or the stations are too correlated together. So it's almost like smoothing your estimates too much. And then too little if you use just the station itself, you'll have too much variability at the station. So it's sort of an in-between. So now we have regional frequency estimates for each station. We want to convert this to a gridded product. The way we do that is to calculate the mean annual maximum at each station. That is taking that AMS series and taking the mean value of it. So you'd have that at the station. We submit these to the PRISM group in Oregon State University, and they'll return sort of an MAM grid from the MAM at the stations. From this MAM grid, we can take our regional estimates at gauge locations. So for instance, the 2-year regional estimate at a gauge location divided by its MAM at that gauge location. Do that at all the gauge locations, interpolate that to a ratio grid, and then multiply that ratio grid times this MAM grid we receive from PRISM, and now you have a 2-year grid. And then you can sort of cascade that and go for 5-year divided by 2-year to get the 5-year grid, and so forth, all the way up to 1,000-year. Lastly, we do the confidence limit intervals. So we use a simulation. I should put it here. It's actually 1,000 simulations to construct 90% confidence intervals at each station. So you do 1,000 simulations and you sort the data, and the bottom 5%, that's your 5th percentile, and the top 95% of that, that's your 95th percentile. And one thing I'll mention that Dr. DeGaetano mentioned is that the confidence limits are actually tighter in volume 2 than compared to the northeastern states, volume 10. And part of that is because there is an algorithm in later volumes that accounted for interstation correlation. So earlier I showed those regions, they were very large regions. When you pull together data and do frequency analysis, ideally you want the data to be independent. Well, when you pull together nearby stations, all events are not independent, they're correlated. So in later volumes, we took this into account into the confidence limit in construction to take the interstation correlation. However, in volume 2, this wasn't necessarily fully implemented, and it also those large region sizes. So that has the effect of being overconfident with the confidence intervals, so they're tighter. And you saw that in Art's presentation. Lastly, we do the peer review, which we send an email to our list servers and other interested parties. They look at the station metadata. They're usually local experts that look at the reasonableness of the estimates, some spatial patterns. And then we publish their questions anonymously, of course, and our answers in the final documentation and make any revisions that are necessary. So what are the major sources of error or the uncertainty? Well, mainly the biggest one is the data. So in the top left corner here, I have, it's the same station. It has 109 years of record, same distribution fitting, all same statistical methods, except I took the latest 10 years, latest 20 years, latest 30, 50, and then the full record, and just calculated precipitation frequency for this. You can see how wide the range is. And as the record gets longer, it converges to a more consistent number. And here it's about 50, but typically it's a little longer than that. But it just shows you how important your data length itself is to your precipitation frequency estimates. I went over quality control. Obviously, these large and actually small values can have a large impact in your distribution fitting. Missing data. So we digitize when necessary. We digitize data to try to extend records. So in this case, this is an hourly station that had in scanned PDF form another 50 years of or 49 years of hourly data from 1900 to about 1948 that we digitized and helped out this area significantly for hourly durations. Spatial coverage, not so much an issue for volume 2, but for something like Alaska, where there's a large data sparse areas, this is a big issue. And methods, they can have a big impact. So in the top left corner here, I have the same data. This station had about 70 years of data, and I fit about, I think, 7 different methods here, distributions, 7 distributions here. And you can see that there's a wide range of, especially 1,000-year estimates, just from changing the distribution, but using the same exact data. I should note that all these distributions pass statistical tests, so they're all technically valid for this fit here. And you still get this wide range. Regionalization method, that can have a big impact. So we had those large regions in volume 2. More recent volumes have had this rolling window of smaller regions. You can also do sort of inverse distance weighting to make your regions and so forth. So that will have an impact. We analyze these statistics duration by duration. So we'll do like a 24-hour, the 2-day, 3-day, and so forth, done independently or kind of independently. So you can get bumps when you look at depth, duration, frequency curves. So we just smooth these out to make them more realistic. And then the interpolation method. So I talked about the prism interpolation. There's many other ways to interpolate. So in the future, everything I've talked about so far, that's all been stationary analysis, Atlas 14. So in the future, we want to enhance this using non-stationary methods. So we did work in collaboration with Penn State University, the University of Illinois Urbana-Champaign, and the University of Wisconsin-Madison. We tested this in Atlas 14 volume 10, which is the northeastern states, partly because it has good data coverage, has a good mix of terrain and coastal areas, and it's I think the highest in the National Climate Assessment, the highest increase of heavy precipitation amounts. So this was a good pilot study place to start with. Funding was provided by DOT, FHWA, and these recommendations will actually be published shortly in mid-2021. I'll just go lightly over this for the interest of time, as we developed the non-stationary process to integrate future climate projections. We had to change our regionalization method and interpolation methods to work in this non-stationary framework. And one of the bigger things here is everything I've shown so far used L moment parameterization methods. We had to change to a generalized maximum likelihood method. This has to do with, Art did a great job talking about the GEV distribution. You have the location, the scale, and the shape parameter. The GEV allows you to add covariates. So you have location, it could be constant in time, or you can add a time varying component to it. So it could be increasing in time, or you just let it increase in time and so forth. We had to change to a generalized maximum likelihood to be able to do this parameterization, because it is very difficult, if not impossible, to do with L moments. Parameters are allowed to vary in time rather than just have a straight time varying component. So instead of just interpolating straight with time, you can have it vary with, say, a future climate projection, mean annual temperature, or mean annual precipitation. We also looked at the partial duration series as an alternative to the annual maximum series. So this is just instead of having 1 point per year, you just take the highest. So if you have 100 years, you could take the highest 100 points, no matter what time they occur. Just talking about the climate models quickly, we have the raw climate models, such as the CMIP suite of models. And then these can be statistically downscaled. A few of these are the BCCA, the LOCA, and the University of Wisconsin-Madison. Dr. David Laurent has what we call the UWPD model. And then there's also dynamically downscaled models, such as the NA Cordex. We use these data sets, LOCA, UWP, and Cordex, but we did discard the BCCA after initial analysis due to an inconsistent dry bias. We looked at the RCP 4.5 and 8.5, and we looked at a quasi-stationary, which is also referred to as a delta method, as well as a fully non-stationary method. And you'll likely hear from Dr. Angel about the quasi-stationary method in the next talk in detail. Time series data, we looked at, like I said, AMS and PDS. And just as an overall result for this is the entire Northeast area average, the percent increase from the reference time, which our reference time is centered at 1975 at a 50-year period. So it'd be 1950 to 2005. Just at a first look, no matter the method and no matter the return period, the 2-year and the 100-year, and no matter the type of emission scenario, they all increase with time. The big difference here is that the quasi-stationary methods that are denoted in the solid colors, the darker colors, compared to the lighter colors, the quasi-stationary are always higher than the non-stationary. And this UWP data set is always the highest. And lastly, the 8.5 is about double the 4.5 if you compare model to model for the same emission, for a different emission period scenarios. So overall, we looked at the 60-minute, the 24-hour, and the 10-day estimates. I just showed the 24-hour in the previous slide. Sorry, I forgot to mention that. The projected estimates for all three durations will increase overall in the future. So there was consistently showing positive. Same with all the different ensembles and approaches and methods, they all showed positive. And we want to adapt this to continuously improve. So most of what we showed is either CMIP5 or downscaled products from CMIP5. We want to be able to use CMIP6 as that matures and is downscaled and so forth. So these are some other additional products I'll just go quickly over. We provide point precipitation frequency estimates, but a lot of times people are interested in regional or watershed average precipitation frequency. And to use that, you need to use what are called aerial reduction factors, or ARFs. And the NOAA-based ones are pretty old, which I have one here in the right here, 1958. Next is a design storm product. So you can go to the website, our website, get the 24-hour, 100-year. It's a single number with confidence interval. But a lot of times the engineers are not interested in just this one number spread over 24 hours. They want to know how it's likely to fall in that 24-hour period. So we want to develop something like that for our website. The confidence intervals, we have fixed 90% interval widths. We want to vary that. And then lastly, a RESTful API so that developers can plug directly into our data. We have this non-standard Python one, but a standard RESTful one would be ideal for developers. And I'll hand over to Mark Glaudemans, my division director now for this part.
Thanks, Mike. And thanks everybody for having Mike and I talk today. Really appreciate the opportunity to speak to you. I just have one slide, but certainly I could talk about this topic for a long time. There's a lot to speak to, but I'll try to condense it into one slide. And certainly Mike, myself, and Sandra, and the rest of the team, we're all available to contact outside and after this discussion. I just want to say a little bit about our development, what's going on right now, and what we're looking to do in the future, what we want to do, what we think we're going to do, what we're not sure we can do, and things like that. And a lot of it follows on the previous speakers. We really appreciate listening to everybody who's spoken to date during this time. You know, we're very interested in a lot of the same things that were expressed here in the last hour or so. So real quickly, the current approach is this is a rare thing. We're in the National Weather Service, the Office of Water Prediction. We're part of NOAA. And we're not used to reimbursable funding. It's not really the way most of our agency executes its mission, but we are a rare sort of corner of the agency where we do rely, this program of Atlas 14 does rely on reimbursable funding. So that may change, by the way, I'll get to that a little bit, but the kind of the buzz line, I will say, it sounds kind of formal and dry, but we respond to stakeholder requests and the sponsorship. And through that, and through forums like this is where it may begin and may continue. But we engage a lot of the local interests, whether that can be, you know, sub-state, multi-state, any different kind of permutation of geographic areas. But we work with the federal highway folks. Mike mentioned that a little bit ago, the Federal Highway Administration, Department of Transportation. We're grateful to their role. They have what's called a pooled fund program where they basically can serve as our conduit to the sponsors. Transferring money in the federal government is very messy. So with their role, it eases that whole process quite a bit. And they put a lot of general oversight and sort of coordination of the larger program as it relates to the Department of Transportation. But their needs pretty much match up with a lot of the needs of the folks on this call. Recently, Mike mentioned Texas, volume 11 at one point. We finished that in 2018. That was a really big effort, a lot of population, a lot of interest down there. And very, very recently, yes, that is just last month and kind of starting right about now, we've just started the next volume with Montana and Idaho. We were hoping to get the 5 states in the Northwest that still do not have Atlas 14 covered, but that did not work out. So we have those 2 states. And then again, based on the feedback, we have a 4-state region. I'm in Maryland, by the way. Most of our Office of Water Prediction is down in Alabama, but this is a little close to my heart. We have volume 13 with it's relatively small geographic area. You can see Maryland, Delaware, Virginia, North Carolina. And then volume 14, Louisiana. Both those 13 and 14 volumes are already been removed from the pooled fund site because the money's been pledged, and now we're just working through the paperwork, which will take some months, but again, we're looking to invoke initiation of no less than 3 volumes. So we're happy to serve the customer needs, but we agree completely with 2 fundamental things. One is that the updates need to happen more often, and they really got to get away from this regional approach, because the bullet there I say the regional approach results in discontinuities at the boundaries and when they're done at different times, and God forbid different methods if some years have passed between the 2. So it's really just not the appropriate engineering way or hydrometeorological or climatological way to do this. So that's sort of the here and now. I want to talk about the future real quick. And as I just said a moment ago, all of us couldn't agree more that we need to do this more often on a regular cycle of 5 to 10 years. And we need to do this nationally. So that's one theme I want to be super clear on. And the other thing is that the last bullet there is we've heard it loud and clear and are preparing to do this, as Mike just talked about, to include non-stationarity assumptions and those enhanced data products. But mostly we're hearing a lot about non-stationarity. That is a big effort to do that nationally, to say the least. That would be a significant effort. There is some prospects if people follow this kind of stuff. There is some legislation right now in Congress. It's been proposed to committee, and if you like looking this stuff up, I'm not a legislative affairs person. I'm a civil engineer, professional engineer, by the way. There's 2 things out there being proposed. You can look it up, called the Precip Act. Precip Act, they made an acronym out of the word precip, and then the Floods Act. So 2 different pieces of legislation that will have to be reconciled, but they're getting bipartisan support. And really that would be a game changer for us. As the director of the team that runs this Atlas 14 development, this is sort of the moment, someone like me has been waiting for, the people before me have been waiting for it, to look for base funding for this through the NOAA mission. There's a lot more to what I just said. Of course, I kept it real simple there with what I just said. But that is where we look to go, again, with volume 12, 13, and 14, still using stationary assumptions. But we want to really break out of that mold once and for all and go national and use non-stationary assumptions. So that's sort of a programmatic finale discussion on Atlas 14. And I'll turn it back to Glenn and welcome any questions.
Yeah, we appreciate it. We do have one more presentation before we do the Q&A period. So Jim Angel. And Jim gives us, he was part of a regional update in Illinois that happened recently. So that's how we got connected with him. And that's part of how this bigger conversation started, is because what they were able to do within that particular section of the country. So Jim has been a climate scientist for 37 years at Illinois State Water Survey, including 20 years as Illinois State Climatologist. Most relevant to today's discussion is that he was co-author on rainfall frequency studies for Illinois in '89, '92, and again in 2020. Other recent accomplishments include being the lead author on the Midwest chapter of the National Climate Assessment in 2018 and co-leader of the 21 Illinois Climate Assessment for the Nature Conservancy. Jim, thanks so much. I think did you recently retire? So you're actually doing this fully on your time. So we really appreciate you being here today.
No, thank you. Yes, yes, I'm emeritus, I guess is the term that you could use for that. But yeah, this has been a great conversation on what's been going on in the region, and great summaries and overviews about the whole process. In fact, I was shuffling slides off camera because there's some points that I was going to make that were already made, so we won't cover that ground. But it's been a very interesting conversation, and I applaud NOAA for the desire to move forward with more rapid updates and taking the nationwide approach, because that's always been my complaint about NOAA Atlas 14. It's kind of this crazy patchwork quilt of old and new studies, and it's just been, it makes, if they'd had better funding all along, it would have been much better to have done nationwide studies. So, but that sounds like that's maybe more promising now that we move forward. So I'm going to talk a little bit about what we did in Illinois here. And I'll share my screen. Hopefully get the right one. Yeah, let's see. So there we go. So we're going to talk a little bit about what's happening in Illinois, and this is work that myself and Mochilo Marcus, who's also at the Illinois State Water Survey, have been doing. So we're kind of joined at the hip on a lot of these projects over the last 10 years or so. And you've already seen a little bit of the more recent work that we've done in terms of climate change and so forth. But I'll kind of back up a little bit and talk a little bit about where we started with on the Illinois study and how it's affected what we've done. So as you've already heard from several of the talks, that with climate change, it invalidates the notion of a stationary time series. So that makes it really hard to use historical data, and it also makes it really hard because you're using these numbers for planning for the future. So looking at future risk. It's not just what's happening right now, but what's happening in the future. So that's made a much more complicated process than it would have been, say, 50 years ago when they, or 60 years ago when they did TP40. And this is true of Illinois. It's pretty much true of the central United States, is that we're seeing increases in precipitation over the last century. For Illinois, we've increased our precipitation by about 4.7 inches over the last century. So we're getting much wetter conditions now than we used to get. So it's not only that we're getting more precipitation, but we're also getting more of the extreme events, and I'll show that in a minute. But what it also does is that when you're in overall wetter conditions, that means anytime you do get a precipitation, a big event, that you get typically more runoff because you have higher soil moisture values. You also have more water in the system, so you get more flooding overall anyway. So these things have been a real problem in Illinois, and it's pretty substantial dollar impact. So if you look at agriculture, we've had lots of years that it's been very problematic, and in the urban areas with stormwater in particular, that's been very much a headache. We did a 10-year study where we looked at insured losses from homeowners and businesses. It was about $2.3 billion in losses for Illinois. So not small numbers by any means. If you look at the more extreme events, this is fairly typical across the many parts of the United States where we're seeing an increase in the heavier rain events. These are the 2-inch rain events per half decade at each station. And so the numbers are a little bit funny, but if you think of them as what's happening every 5 years. So on average, in the early part of the 20th century, you'd get maybe 1 to 2 or 1.5 events, 2-inch rain events per half decade. And then you get to the second half of the 20th century and on into the 21st century, you see that frequency has increased quite a bit. So now we're about up to 2 events per decade, whereas some of the, compared to some of the drier parts of the early 20th century, it's almost doubling in the frequency of those 2-inch rain events. And 2 inches is kind of a, it's not a, it's kind of a rule of thumb in that that's about the threshold of where you start seeing flooding problems. So that's where you start to see basement flooding and street flooding and farm field flooding and things like that. So it's not set in stone, but that's just kind of a nice threshold for tracking that. So in looking at this, we decided for Illinois that based on the previous graphs and other research and data like this, that we were not going to use the earlier part of the 20th century. We're actually going to set that aside and focus primarily on records after World War II. And so that gave us a better picture of what the current wet climate looks like. So the problem is if you incorporate all that earlier stuff that's dry, it tends to drag down the numbers. And in fact, I think that's part of the explanation for why we saw some relatively low numbers in NOAA Atlas 14 compared to Bulletin 70 and 71, or in particular, was that they used a lot of stations that had records from the early part of the period that kind of held down some of those numbers. So our solution to the observed changes were, like I said, we used the more recent data from 1948 to 2017 that represents our current wetter climate. And the bonus for that is it also gives us about 3 times as many stations from 1948 onward. And this is pretty much true across the Midwest. post-World War II, there's a big expanse in the number of available stations. And so that gives us better spatial coverage than just looking at the long-term records that extend farther back. They also included a Bulletin 70 style adjustment for giving more weight to the second half of the record, and I'll talk about that in a second. But all we're trying to do is just make sure that we're representing at least the current wet climate in this particular study. So we ended up with about 176 stations in Illinois that had at least 30 years of record from this time period, 1948 to 2017. And you can see there that it's pretty well covered across the state. Many of these stations actually had many more years than 30 years of record, but that was the minimum threshold that we used. So 176 daily stations, had about, I think about 86 hourly stations. The hourly data has a lot of problems. There's not good spatial coverage. There's a lot of missing data. And the data we do have, when you do the analysis, sometimes the results are a little flaky, I guess you'd call it. So as a result, what we did is we didn't use this data directly, but we used it to calculate ratios of the 1 day to the X hour event. So we actually converted the 1 day to 24-hour events, and then we used ratios to calculate the 12-hour and the 6-hour and the 3-hour and so forth. And that gave us a fairly stable results. And it's actually those ratios have been used in Bulletin 70 and Bulletin 71 and NOAA Atlas 14, and the numbers, those ratios have actually been pretty consistent across all those studies. So the advantage of that also is it gives you you get a nice continuity between the 24-hour values based on daily data and the sub 24-hour based values, whereas you wouldn't necessarily get that if you mix the daily data and the hourly data together. It makes for a much cleaner transition there. So we use the L-Moment software, and as we've kind of seen in some of the other presentations, this has been pretty universal, I'd say, in the last 25, 30 years of using L-Moment. So was kind of the go-to software, easy to use, lots of features that you can tap into, look at multiple distributions and so forth. But this is actually a plot from one of the atlases, NOAA 14 atlases, that I actually was using just to show the types of distributions you could use and color coded, but also that shows the other problem that we've had with L-Moment software, at least in Illinois, and that is that it struggles with the longer return periods. And I kind of half jokingly call the rainfall distribution in Illinois as kind of a dog leg distribution, and that it seems to fit the more traditional distributions up to about 10 to 20 years, and then it takes a turn to the north, and we've actually need almost a different kind of distribution to fit the numbers above 20 years. So the problem is that with L-Moments, if you just left it to its own devices, it tends to really underestimate the longer return period values. So what we did in this study was we used a couple of different statistical techniques and also some professional judgment on adjusting those curves upward to match the observed data that we had available. So that was actually one of the more surprising things, or maybe disappointing things about L-Moments. Is I thought in the beginning that this was going to cure all our problems, but it turns out it actually doesn't solve everything. So we actually focused our Illinois study on regions. There's a couple reasons for that. One is that the old Bulletin 70 used these 10 regions. It's also in many of the regulatory instances in Illinois, most of it's focused on municipalities or very small drainage basins, so that having things on county boundaries is not a problem. In fact, it's probably the most useful of all the combinations. We could have used gridded data. There are some challenges there. One is that from a regulatory standpoint, you know, if you're in one town or the next town over, you get slightly different numbers, and maybe that's not desirable to have that if you're looking at the bigger picture. Also, sometimes with the region, if you do the spatial analysis, you get little artifacts in the data that may or may not be totally relevant to this. So, for example, we had the case of our Urbana station, which was literally right behind my office, being exceptionally low in some of the historical studies. And we could never figure out why that was. Well, it kind of just turned out that it just had not had the really big rains that some of the other nearby stations had. And finally, after we did Bulletin 70, they got their big rain event, and then the numbers matched up more closely with the surrounding stations. So you get that whole sampling variability going on there that can lead to spatial patterns that may or may not be relevant. So we went with the regional values for that. We also did an adjustment for non-stationarity. It's kind of like what we did in Bulletin 70. What we did is we used the ratio of the 1983 to 2017 period divided by the earlier 1948 to 1982 period. So we already picked the wetter part of the longer record, and then we gave even more weight to the more recent period. And this was kind of a compromise. We used the longer record so we can actually calculate the longer return period estimates a little better. But by using this ratio, we could actually give even more weight to that more recent period. So I would say it's a fairly aggressive adjustment. This is for, what I got highlighted here is for northeastern Illinois. And on average, it was about a 14% increase over that time period, which matched the trends that we're seeing in heavy precipitation in that region. And in fact, if you look at the old Bulletin 70 on the left here, the 100-year 24-hour value was 7.58 inches, and now it was almost an inch more compared to that earlier values. And strangely enough, the NOAA Atlas 14, which landed in between these two in age, actually got, I think, 7.31 inches. So again, I'm not 100% sure why the NOAA Atlas 14 was typically lower than what we saw in Bulletin 70 and also in Bulletin 75. That's the new study here. I think part of it was that L moments issue we talked about, and part of it was that they didn't recognize the non-stationarity of the time series. So really for Illinois, the Bulletin 70 was the standard up until the new study came online, and now it's the standard, the new standard for all projects in Illinois. And all those values are higher at the longer return periods than what we saw in NOAA Atlas 14. As mentioned earlier, we also revisited the so-called Huff curves, which is the time distribution within a storm. We had two smaller networks that very high density with high resolution data that we could use to calculate for at least for smaller regions what the time distribution was within the storm. And in reality, they're pretty darn close to the kinds of numbers that we saw in the original Huff curves. Huff curves were actually done back in the 50s and 60s using some high resolution networks that were available at the time. And for the most part, those numbers haven't changed radically. So that's, I guess that's good news in that regard. So that's used a lot in terms of timing of storms within the models. Also, we did some additional work on looking at changes in the future. And then we've, as we talked in the previous presentation there, we've done some work on that already. And I just want to say that in the most recent Illinois climate assessment, we looked at projections of future precipitation changes, and overall we're expected to be wetter. And with the future scenarios, the top row is there's the lower emissions for mid to late century. The bottom panel is higher emissions for the mid to late century. And overall, the lower emissions scenario gives you wetter conditions, but not as wet as the high emission scenarios. And the numbers at the end of the century are always higher than what they are at mid-century. So in other words, the effect of future climate change on precipitation gets stronger the farther out you go. This is the same story for the frequency of 2-inch rainfall events in Illinois. So there's the graph of historical data on the left side, and the same layout on the right side on the lower and higher emissions. So the frequency of those events gets higher, not only the farther out you go, but with the higher emission scenarios as well. So that brings up some interesting questions. And in fact, we've also kind of alluded to some of those early on. One is that there are some issues with the modeling. You know, those heavy rain events tend to be very intense and somewhat more localized than broad bands of rain. That's not the strong suite of climate models. And so there are some biases in that, a dry bias. We can make adjustments for that. And as we talked about a minute ago, is that University of Wisconsin data set, I think in our work, has done about the best job of adjusting for that dry bias. But even if you had a perfect model, we still have uncertainties on future emission levels. We've done work with the RCP 8.5 and the RCP 4.5. Probably the thinking right now is we're probably going to land somewhere in between those moving forward. But that does give you considerably different numbers especially as the farther out you go. So just kind of give you an idea. This was a 2-year study for us with about 295K for the comprehensive update that included the Huff curves and a few other things that we looked at as well. Unfortunately, that study in particular for Illinois only had money for updating the numbers using the historical data, so up to the present time. But we have looked at techniques to address at least the historical climate change, and there's quite a bit in that report on techniques that we looked at to address climate change issues, and then also this issue of the underestimation of the longer return periods from L moments. But I think that's probably the questions that we've been wrestling with on this all along for probably the last 30 years is how do you adjust for climate change? There's no real standard, there's no real textbook answer for that. So you kind of have to work through this and try to address it as best we can using the best data that's available to us, both historical and the projections from models. I think probably, speaking philosophically, at some point we'll probably have to get away from this idea that we're going to have one number that we can mandate, you know, like the 100-year 24-hour value is that you'll design for is 8.7 inches. I think at some point we're going to have to think more in terms of, you know, in terms of probability and risk analysis of, you know, what's likely to happen, what's the worst case scenario, and things like that. So I think we'll probably have to rethink some of the how we do things moving forward. But for the Illinois study, it was beyond the scope of the study, as they say. So we came up with the values that we think best represent the current conditions in Illinois. And one alternative is to, if you were to do a study like this in Ohio, is to do the historical analysis and taking into account climate change, and then say, okay, well, here's what you want to do if you just want to use historical data. Here's some additional things to consider for future climate change. So maybe that's one way to address some divide between who wants to just use the historical data and who wants to use the future projections. So I'll leave it at that. And I also, at the very end, I have some references here that I guess hopefully it'll be sharing this presentation along with the others, but I'll put them up here just so you can see those and turn it back to the host.
Thanks, Jim. Really appreciate you being on today, taking time out of your personal day to share with us the work that you've done most recently with Illinois and how it relates specifically to the endeavor, at least we're considering here in Central Ohio, or maybe all of Ohio, or maybe even multi-state. But appreciate that very much. You're very well published. I was looking up some other things, and every single study that had anything to do with in this region, you were almost on all of them. So
Yes.
Appreciate all the great work you've done throughout your career.
Thank you.
I think all of the speakers are available. We can do a Q&A. I know there's been quite a few things going through the chat, and if you haven't looked at that yet, please do. Brooke has given some housekeeping stuff for you, including an opportunity, I think, to do a survey. We're also trying to find out, how many folks would be interested, maybe in a longer term. I'm going to share my screen real quick. I got a couple contacts on here for you, so I'm going to share that with you while we talk as we lead up to these questions. So you've got Matt with City of Columbus and Brooke with MORPC on there, their email addresses. Certainly reach out to them if you'd like. There's probably an opportunity through some of the surveys, maybe for you to respond with your interest in continuing to be contacted to consider this going forward. And I appreciate we're still at almost 100 people, and we were at 100 up to Jim's finishing here. So you've all stuck through us for the entire event, and I really appreciate that very much. All right, so hopefully you've got that information. I'm going to stop sharing that so we can see each other again. And Brooke did say she was going to monitor the chat. Start putting some of your questions in there if you haven't done so already. One of the questions I had was for Mark. Any clue if the legislation has got legs like they say? I mean, is this thing have any chance of passing? And if it does, what does that realistically mean to this nation as far as having our modeling updated and any regular recurrence? Do you have any feel for that yet? I realize it's completely conjecture, but just kind of trying to figure out what that might mean to us.
Yeah, Glenn, it is conjecture, but I'm a person that has opinions and hopes, right? And maybe my public affairs folks wouldn't like this, but I'll offer some unofficial comments. The prospects look encouraging. I'll say that in a very measured way. Again, I intentionally referenced the legislation by its name. It's Precip and Floods Act, and it has gotten consideration last year in the last Congress and just over the last couple months. And if it goes forward, as the legislation is published, and you can read the legislation, it's not just about our Atlas 14, by the way. It involves quite a few other things important to our water resources program in the National Weather Service. If it goes forward, it's a authorization legislation. It's not an appropriation, but those things can often follow, right? And if it were to be adopted as an appropriation, it would be a major change in the way the Atlas 14 work could proceed, and would really open up the prospects for doing, again, that national update on a recurring basis on not just these 10-year or 30-year climate cycles, but really that less than 10, more than 5-year type cycle. So it would be to talk folksy, it would be a game changer.
Thanks for that update, that information. I would think there'd be a lot of things that this Congress would be interested in pursuing as far as a program like that. A lot of valuable information would come out of that, and so much has already been mentioned already on this in the last 2.5 hours we've been together today. Is there any questions coming through right now? Let's see.
It looks like Glenn, this is Brooke. It looks like we've had some good conversation regarding how some of that pooled funding works for some of the Atlas 14 work in the different regions. And it looks like folks have popped on and answered those questions. So there's definitely a lot of kind of both question and answering going on in the chat if folks want to look there. I noticed we got a Franklin County Public Health looks like they want to continue to be engaged in this effort. So yeah, definitely if you're interested in continuing to work on this, definitely either email, you can pipe up in the chat or email either Matt Repasky or myself, Brooke White at the Mid-Ohio Regional Planning Commission. But yeah, it looks like a lot of the questions are being answered within the chat itself.
Very good. And the speakers, you're welcome to ask questions of each other. I know you've all been on the entire session from beginning to end. I started us off, so I'm willing to let the stage for somebody else to ask a question now. It's like one of my staff meetings. It's nothing but crickets. Everybody's on, and everyone's engaged up until the point where you ask them, okay, now it's your turn, and then crickets. Okay, well.
I'll just add, Glenn, this is Mark. I'll jump in. Again, if we can expand the program, we're looking for some academic and within NOAA and possibly outside NOAA sort of connections. We always take very, very seriously our peer review process for Atlas 14, and the methods we would be adopting would be something that we would want the community to understand and accept. So some of the people on this call are, like you said, are very highly referenced and value their opinion.
I think you'd get some great contributions from the folks that spoke here and the folks that are just in attendance. Thanks for that offer.
Okay, so it looks like we have a note from Casey. He was asking if everyone is aware of the work of the runoff curve number group and the potential changes to the RCN methodology, and talking about the fact that what they're considering is pretty profound. Casey, you can feel free to take yourself off mute if you want to raise this up as an important methodology update that might be considered in any work going forward.
Uh-oh, he's got no mic. It's not going to work then.
Oh.
All right, well, great session, great attendance. I think and continue to work through the chat as long as you'd like, but I want to kind of close it down for those who would like to move on with their day. We appreciate your attendance here today, for your time. We appreciate all the speakers for the great expertise and knowledge that they've shared with us, and trying to wrap our heads around what it would mean to do an update throughout our region, or even even broader than that. This has been very, very helpful. We appreciate all the partners, both locally and further out. Please reach out to Brooke or Matt or myself, anyone, if you're interested in continuing this conversation. And also please respond to the survey that we'll have after this. And then the other thing from Brooke at Franklin Soil and Water, she did say that I think they've got the CEU type information that's going to be coming out in a week, and we have recorded the forum today, so that'll be available to attendees as well. With that, if you need to go about your day, certainly do so. I'm going to stick around for a couple minutes, see if some more questions do come through, or if anyone wants to take it. But I did want to give everyone kind of that closing bit right now, and appreciate your attendance. Brooke and Brooke, thanks so much for all your coordination, everything you've done to make this happen. And thanks again to the speakers. I think we can go ahead and end the forum at this time. And again, we really appreciate your time and efforts to prepare for this discussion today, and for willing to share your knowledge with the rest of the group. Thank you.
Great.
Thank you so much for moderating, Glenn.
Yes,
No,
thank you.
yeah.
Fun.
My pleasure.
Thank you.
Thank you, everybody.
All right.
Take care all.